Hello students, welcome to the 21st lecture on particle physics, and we are going to talk about CP symmetry in weak interaction processes. Let us start with the example that we discussed on the last turn, where we had pion decay. A pion was decaying into mu minus, pi minus is decaying into mu minus and nu mu bar, or pi plus is decaying into mu plus and nu mu. And what we had discussed is that pion is a spinless particle, and since this decay is taking place at rest, therefore muon and neutrino, they have to exactly move in the opposite direction to conserve momentum, and to conserve spin, the angular momentum of these two particles should also be directed in the opposite direction. Since neutrinos are always left-handed, therefore, as you can see, the momentum and spin of the neutrino, they are in opposite direction. And since neutrinos are left-handed, therefore it is forcing mu plus also to become left-handed, and this process has been experimentally observed. Now when we apply parity operation, then parity operation does change linear momentum. It does not change angular momentum. Therefore, they are unchanged, while the angular momentum is not changed. I'm sorry for that. While the linear momentum changes to minus p, and therefore mu plus, which was going in the downward direction, now it has started going in the upward direction. And similarly, nu mu, which was going in the upward direction, is now going in the downward direction, while spins are unchanged. Therefore, what is happening? The direction of momentum of the neutrino and the spin, they are along the same direction, and therefore a neutrino is becoming right-handed. And since we know that neutrinos are not right-handed, they have not been observed as a right-handed particle, therefore this is not an observed process. Similarly, if we think of charge conjugation does not see the linear momentum of the particles or the spin of the particles. Therefore, they will be unchanged, while particle will be changed to anti-particles. Therefore, pi plus will be changed to pi minus, mu plus will be changed to mu minus, without any change in location or momentum or angular momentum, etc. But what is happening, that when we are applying charge conjugation operation, nu mu is becoming nu mu bar, and this nu mu bar is left-handed because momentum and angular momentum, they are unchanged, and this has not been observed. But we combine these two operations. Either we take from this side where we had the parity operation. Now when we apply charge conjugation operation here, then pi plus will change to pi minus, mu plus will change to mu minus, and nu mu will change to nu mu bar. And this nu mu bar, as you can see, is now right-handed, and we know that antineutrinos are right-handed particles. Therefore, this has been observed. Therefore, what we are seeing, that in pion decays, Cp is a good conservation law. But this is not in general true in all the cases, and we are going to discuss a few cases where Cp gets violated. And I'm going to talk about Keon oscillation phenomena, or this is also known as Keon regeneration phenomena, and finally to the observation of Cp violation in the neutral Keon sector. But besides neutral Keon sector, this violation has also been seen in B0 sector and other D0 sectors. Therefore, In general, we are going to start with neutral kaon sector. And what we know in the case of neutral kaons, that they are members of pseudoscalar meson nonet. There are two neutral kaons, K0 and K0 bar, with strangeness +1 and -1, having the same spin and parity as shown here. And similarly, we can have K0 star and K0 bar star, except the case that they are vector particles, spin 1 and parity odd. Now, if we recall, the masses of the kaons, K plus is 493.67 MeV. It is made up of US bar quark because its strangeness quantum number is +1. Therefore, we must have S is equal to, we have S equal to -1, then S bar will be +1. For K0, the mass is 497.6. It is made up of ds bar quark. Its strangeness quantum number is also +1. Then we have K0 bar, which is antiparticle of K0. Mass will be the same. While quark content here, K0 bar is a strangeness -1 particle. Therefore, it is d bar s. And K minus, again is strangeness -1 particle with the quark content as u bar s. But we will see that while propagating, K0 and K0 bar, they don't propagate as independent states. They propagate as an admixture of states that we will call it as K10 and K20. And this K10, K20, we will rechristian it by the name KS0 and KL0. S stands for short-lived kaons and L stands for long-lived kaons. And these are the decay modes of the kaons. Therefore, we have the production state as K0, K0 bar. Then the propagation states K10, K20, and the decay states are KL0 and KS0. Now, what we know about the kaons, that they may be produced via several ways. And here I have taken the examples of kaon production in strong interaction processes, where, for example, in the first case, you have a pion beam and it strikes proton target, and we have K0 and lambda 0 as the final state particles. If you recall, pi minus plus p proton is giving you K0 plus lambda 0. Isospin, pion is an isotriplet. This will be 1. Proton is an isodoublet. K0 is an isodoublet. It exists with K plus. And lambda is an isosinglet. Therefore, you can see that 1 plus minus half will give you half in the final state. Then I3, pi 0 has the third component of isospin as 0. This is plus half. And then you have K0 and lambda 0. This is an isosinglet. And so this is pi minus. This pi minus has I3 minus 1. Therefore, this K0, which is a member of K plus K0 doublet, I3 is plus half for this and minus half for this. Therefore, this is minus half. We see that we are conserving I as well as we are conserving I3. This is a strong interaction process. The other important point that is important here is the following. Strangeness of pion is 0. Proton is 0. K0 has got plus 1 strangeness and lambda 0 has got minus 1 strangeness. Therefore, strangeness in a strong interaction is also conserved. Therefore, these are strangeness conserving processes. Electromagnetic interaction is also a strangeness conserving process, while I as well as I3, they are conserved. Now, similarly, if we take another example of P plus P bar going to K minus K0 and pi plus. You see, I is half here. P bar and N bar are member of iso-doublets. This will be half. This is half. This is half. And this is 1. As you can see that 1 and half can give me us half and 3 half. And half and 3 half with this half can give me 0, 1. And 3 by 2 will give me 1 and 2. Therefore, the possible values are 0, 1, 2 in the final states. And here the possible values are 0 and 1. Therefore, we are conserving I. Similarly, if we look at I3, then I3 is for proton is I3 for proton is plus half, antiproton is minus half, and K minus I3 is minus half, K0 I3 is minus half, for pi plus I3 is plus 1. Therefore, you can see that plus half and minus half will be 0, and here minus half plus 1 algebraic sum will be 0. Therefore, you are conserving I, you are conserving I3. This is a strong interaction process. Besides that, if you look at the strangeness, then proton and antiproton are non-strange particles, and therefore the strangeness quantum number will be 0 for proton, 0 for antiproton, minus 1 for K minus, for K0 it is plus 1, for pi plus it is 0. Therefore, you are conserving strangeness also. Therefore, what we see that all these examples which have been written here, they are producing K0 and K0 bar through strong interaction processes. You can also produce K0 and K0 bar through electromagnetic interaction process, through weak interaction processes. Therefore, the production mode of K0, K0 bar can be all three: strong, electromagnetic, as well as weak. As we have discussed, K0 is a strangeness plus 1 particle and K0 bar is a strangeness minus 1 particle, and that means they are particles of definite strangeness, they are particles of definite parity, they are particles of definite masses. Now, under parity operation, since we know that Q is a pseudo-scalar particle, therefore when the parity will operate on K0, we will get a minus sign. Similarly for K0 bar, this is what I had told you, that these are members of pseudo-scalar non-net. Pseudo-scalar stand for spin 0 and parity odd particles. Then we apply charge conjugation operation. Charge conjugation operation will take K0 to K0 bar and K0 bar to K0. Now we combine these two. As you can see that here, if I combine, this will give us Cp K0 is minus K0 bar and Cp K0 bar, this will be minus K0. What you realize that when Cp is operating on K0, you are getting K0 bar, and Cp is operating on K0 bar, you are getting K0. Therefore, if you look at all these three examples, then K0 bar and K0, they are the definite Cp, definite parity eigenstates with eigenvalue -1, while here you are, when you are operating by C, you are getting K0 bar, or when you are operating C on K0 bar, you are getting K0. Therefore, which implies that K0 and K0 bar are not definite C eigenstates. Similarly, when we are talking about Cp, we are getting K0 bar, Cp being operated on K0, and Cp being operated on K0 bar is giving me K0. Therefore, it is also not eigenstates of Cp operator. That is what we have written here, that K0 and K0 bar are also not definite Cp eigenstates of the combined operation. Now we form a linear combination of K0 and K0 bar such that I am calling one as K10 and another as K20, such that with a normalization factor, this is K0 plus K0 bar, and K20 is 1 by root 2 K0 minus K0 bar. Now we operate by Cp here. What we will realize that Cp get operating on K0 state, you notice that K0 will change to minus K0 bar and K0 bar will change to minus K0. You take minus sign common, you have K0 plus K0 bar, and that means this is nothing but minus K10. Similarly, you can see that when Cp operating on K20 will give us 1 by root 2 outside minus K0 bar plus K0, because this already a minus sign is there. Therefore, the sign will get flipped because of a minus sign here when Cp is operating on K0 bar. If I take, this is 1 by root 2 K0 minus K0 bar, and this is nothing but K20. Therefore, when Cp is operating on K10, it is giving us a -1 eigenvalue, and K10 is an eigenstate of Cp operator, as well as in the second case, the eigenvalue is +1, and K20 is also an eigenstate of Cp operator. Therefore, you can see that Cp operating on K10 is giving us minus K10, and Cp operating on K20 is giving us plus K20. That means eigenvalue in the first case is -1, and in the second case it is +1. That means K10 and K20 states are definite Cp eigenstates with eigenvalues -1 and +1 respectively. Now the important point, as you can notice here, that we have formed K10 and K20 from the combination of K0 and K0 bar. While K0 and K0 bar are real particles, while K10 are not particles and anti-particle states, therefore their masses as well as lifetimes may differ. The K mesons decay either into 2 or 3 pions. Since the pions have negative intrinsic parity, they are pseudo-scalar mesons like kaons, and the 2 pion and 3 pion states are in S states for kaons decaying at rest. Therefore, what will happen? The 2 pi states will have a Cp parity equal 2 pi equal to +1, and 3 pion states will have Cp parity as -1. If you recall, pi plus, pi minus, we are operating by Cp. Then we know that this can be equivalently written as charge conjugation operation operating on pi plus. This will give us a minus sign, and pi minus, this will give us pi plus. Therefore, this will become pi minus pi plus, and that will be equivalent to a reflection. Therefore, this is minus 1 to the power L, and then you have from the parity of the two pions. Therefore, the overall you will have a sign positive, while for 3 pion states, similarly you have parity of pions as odd, you will pick up a minus sign from there. Therefore, in the 2 pion case, the Cp eigenvalue for the 2 pion states, that is plus 1, as they are states where L equal to 0. That is an important catch, that your L is equal to 0. Therefore, when you are talking about minus 1 to the power L, that will be minus 1 to the power 0, and that is plus 1 here. Similarly, here you have 3 pions, minus 1, and minus 1, and that 3 minus 1 is giving you minus 1. Otherwise, from the C operation that you are getting is again a quantity that is consistent with L equal to 0. Therefore, mind it that when we are talking about charge conjugation operation, we have P pi plus, P pi minus, and the reflection. Therefore, what we have, minus 1 to the power L times parity of pion as minus 1, parity of pi minus is minus 1. This minus 1 to the power L is coming because we are interchanging pi plus by pi minus because of C operation, and this is S state. Therefore, this is minus 1 to the power 0 times plus 1, and this is plus 1. While when we have got 3 pions, we'll say pi plus, pi minus, and pi 0, then there will be a parity for pi 0 also, and this quantity will change to orbital is parity of first the angular momentum between 1 and 2, and that will add to the third one, but it is consistent when this total angular momentum is 0. Therefore, you will pick up a minus sign for 3 pions and a plus sign for 2 pions. That means if you look at this, the previous case, Cp eigenvalue for K10 is minus 1, while Cp eigenvalue for K20 is plus 1. And we are seeing that Cp eigenvalue for 2 pions states is plus 1, while for 3 pion states is minus 1. And this implies that Cp, if there is a Cp conservation, then K10 should decay into 3 pion decay because Cp eigenvalue is minus 1, and K20 should decay into 2 pion state. Now, when we are talking about K10 and K20, 3 pion and 2 pion state, you are creating 3 pions. That means you need more phase space in the case of K10 because you have to create a mass of 450 MeV, while here you have to create a mass of 300 MeV approximately. Therefore, here you have available more phase space. Therefore, decay of K20 into 2 pions will be much faster than the decay of K10 into 3 pions because the phase space that is available to you is smaller in the case of K10 than in the case of K20. And that is why K20 has a shorter lifetime of approximately 89 picoseconds, or say 0.89 10 power minus 10 seconds. And the long-lived kaon K10 has a lifetime of 51 nanoseconds. Therefore, if you look at it carefully, tau s is 89.2 picoseconds and tau L is 51.8 nanoseconds. That means if I talk about tau s by tau L, then this is equal to 89.2 into 10 power minus 12 upon 51.8 into 10 power minus 9. This, in the denominator we will have 1000, and this will result a large value in the denominator, because simply you can see that this is the denominator is a large quantity. Therefore, tau s by tau L will be equal to 1 upon say 570 or something like that. That we will discuss later in this class. For this reason, K10 is called as KL0. We are rechristening the name. We are calling it by the name KL0, the long-lived kaon, and K20 as the short-lived kaon. Therefore, instead of calling it as K10, K20, we are calling it by the name KL0 and KS0. Therefore, instead of writing as K10 and K20 as K0, now we have started writing this K0 as 1 by root 2 KS0 plus KL0 and K0 bar as 1 by root 2 KL0 minus KS0. This was K0 minus K0 bar, if you remember correctly. Since strangeness is not conserved in weak interactions and both K0 to K20 are neutral particles, therefore it was suggested that while propagating, K0 may get converted into K0 bar and vice versa. Therefore, what we are saying that K0 can get converted into K0 bar, or K0 bar may get converted into K0, because strangeness is not conserved in weak interaction processes. So therefore, through weak interaction, K0 can get converted into K0 bar, or K0 bar can get converted into K0, but this cannot be a one-step process because the overall change in strangeness is of 2 units. And that we are going to talk about. However, this transformation of K0 to K0 bar or equivalently K0 bar to K0 is not possible in the first order at the tree level because of delta S is equal to 1 rule. And simply before going ahead, just let us talk about delta S is equal to 1 rule. Suppose if I talk about a neutron decaying into proton plus electron plus antineutrino. Now, what is neutron? Neutron is made up of 2 d quarks and 1 u quark, while proton is made up of 2 u quark and 1 d quark. That means what is happening in the beta minus decay? A d is changing to u. How can a d change to u? This has got baryon number 1 by 3, charge minus 1 by 3 in units of electronic charge, while this guy has got baryon number 1 by 3 and charge plus 2 by 3 in units of electronic charge. This can happen if this fellow emits a W minus and that gets converted into then a U quark. Therefore, a D quark is emitting a W minus and it's getting converted into U, and as you can see that total baryon arriving at this junction at this point is 1 by 3. Total baryon leaving from this point is 1 by 3 as the baryon number of U quark, while the total charge leaving from this junction is plus 2 by 3 for U quark and minus 1 for the D quark. Overall, this is minus 1 by 3. Therefore, this was the charge arriving at this junction. Therefore, what this is doing, this d quark is emitting a W minus, and it is being converted into a U quark, and this W minus then what it does, it gives rise to, let me write here, electron antineutron. Therefore, to complete the diagram, the neutron decay at the quark level, you can show it by the following diagram. This is UDD, a neutron, getting converted into U remains U, this D remains D, and this, the other D fellow, this is getting converted into U. Therefore, you have UDU, and this is emitting a W minus, and this is giving rise to E minus nu E bar. This is known as the Feynman diagram for the process neutron decaying into proton plus electron plus antineutrino. Similarly, you can also think of proton decay inside the nucleus in terms of at the quark level in terms of Feynman diagrams. Now, what is proton decay? A proton gets converted into a neutron. Besides that, it emits E plus and a neutrino comes out. Therefore, the process is a proton inside the nucleus is getting converted into a neutron plus E plus nu E. This is a beta plus decay process, what is known as beta plus decay or positron decay. And as you can notice, this is UUD getting converted into UDD. Now, how come a U can get converted into D? This is possible only when a U emits a W plus, then the baryon number is 1 by 3 for U, D is 1 by 3, the total charge arriving at this junction is plus 2 by 3 in units of electronic charge, and the leaving from this junction is plus 1 and minus 1 by 3, that will make plus 2 by 3, and then this W plus is giving rise to E plus, an antiparticle is represented by an arrow in the downward direction, and a particle is represented by an arrow in the upward direction. Therefore, you have at the quark level this process. The others are UDU and this is DDU. Therefore, DDU, UDU, a proton is getting converted into a neutron. Therefore, these are the Feynman diagrams at the quark level. Now, this is about the non-strange particles. But if we talk about strange particles, then in the case of strange particles, if you notice, and we will discuss this in great length in the next unit, where we will have the leptonic, semi-leptonic and non-leptonic decays. But for the completeness sake, to understand delta S is equal to 1 rule, just let me give you another example, that a lambda particle is decaying into P plus E minus plus nu E bar. Now, what is a lambda particle? It is made up of UDS quark. What is a proton? It is a UDU quark. Therefore, S is changing into U. And S has got a charge of minus 1 by 3. U has got a charge of plus 2 by 3. Therefore, at the quark level, S quark is changing to U quark. The others are UDS. And this by emitting a W minus, and this W minus is giving rise to an electron and anti-particle, downward arrow. Okay, this is an outgoing anti-particle. Anti-particle is represented by a downward arrow, while outgoing particle is represented by an upward arrow. Therefore, this is the decay process. But what has been found out, that the decay of neutron to proton, electron, antineutrino is different. Decay rate is different from the decay rate of lambda going to p plus e minus plus nu e bar. And this we understand by the fact that strangeness here is -1, here is 0, and charge here is 0, and here it +1. Therefore, delta S, final strangeness minus initial strangeness, is +1. Final charge of the hadron minus initial charge of the hadron is +1. Therefore, if this is delta, while in the case of neutron, decaying into proton plus electron plus antineutrino, this strangeness is 0, while charge is 0 and +1. Delta Q is +1. This is 0. Therefore, this is an example of the process where there is no change in strangeness. This is possible a process where there is a change of strangeness. Therefore, this is a strangeness changing process, and this we will talk about in the next unit, that the strangeness changing processes are Cabibbo suppressed than the non-strangeness changing process, what in literature is known as strangeness conserving processes. Therefore, this is an example of strangeness changing process. Then let me take another example. In principle, that should be possible from the phase space criteria, that if I talk about a cascade 0 decaying into proton plus electron plus antineutrino. As you know, cascade 0 is a spin half baryon. Therefore, this is a baryon, this is another baryon, and you are conserving baryon number. You are conserving charge. But what is happening? This guy is USS, this fellow is UUD. Therefore, what you require is the conversion of 2s to 2 non-strange quarks, and this process is forbidden. Therefore, the delta S is equal to 2 or delta S is equal to 3 processes, they are forbidden, because another example is omega minus decaying into n plus e minus plus nu e bar. Here you can see that 3s quarks getting converted into 3 non-strange quarks, and this is a forbidden process, because we will talk about it, that 3 W exchange diagrams or W exchanges will be required, and that will be highly forbidden process. Therefore, here we are talking about when K0 to K0 bar conversion, we have to keep in mind that K0 is a strangeness +1 particle, K0 bar is a strangeness -1 particle. The overall strangeness is of 2 unit, and this is in general at the tree level is not allowed. Tree level means by the exchange of a single W exchange diagram. This will be possible when there will be 2 W boson exchanges, and we shall talk about this in the next lecture. Thank you very much.